Okay, good afternoon. This is the second lecture of RF and microwave circuits and systems in the winter term 22-23, dating October 26, 2022. This is a only virtual lecture. We will start with some basic ideas of communication, and in a relatively short video, I will try to give you that information. Before we do that, I would like to wrap up our item of applications, which was that we were looking at communication and sensors, and the sensors especially took our interest because it is microwaves can help us to provide safety, which is a very general term, but as we will see very soon, this is a term which can be broken down to sensors and especially a combination of sensors. So, for example, if you look at a car in a relatively simple top view, you have various things that we want to talk about. For example, we had this overtaking help where there is a critical problem that maybe is a relatively small object like somebody on a motorbike has to be tracked very close to us. And that is a task which is important because if there's a mistake in this sensing or false warning, that can cause significant problems. And what can we learn from that? So first of all, we have all kinds of environmental things. For example, there's the blind spot detection here, which we just looked at. And then there are more simple things like the object detection. So, for example, something is standing behind you, which can be also can be looked at from the perspective of an standing object. Then the more difficult thing is the side impact, where something comes from the side. The typical story of this is that this is extremely close to us, and we are very vulnerable. So there should some additional airbags should go up. And then to the front, there's all kinds of things which you can do. There's the adaptive cruise control, which is essentially a radar looking forward and giving you a distance to the car in front of you, or maybe some traffic jam. And if you find that odd, I can only say that in any lorry which is deployed to the street today in Europe, this is a must. So this adaptive cruise control system, for especially with the stop and go option, is something which in lorries at least is built in. And then we have all kinds of object detections which require additional features. And here there's now the dedicated idea. There are several ideas which are called safety. So first of all, there's the idea that atmosphere is sometimes not opaque to us, so we have trouble in looking through clouds. Water is absorbing heavily, but optical signal. That's why in the clouds we can't see through them. On the ground, we call this fog, and that is very dangerous. And that's why, and microwaves are also absorbed strongly in this fog, but they still penetrate. Yeah? So we still have a chance to have an object being seen through that cloud. What you also can learn is there's different ranges here which we need to accommodate. So 200 meters for the forward-looking radar. This is mainly based on our reaction time. It takes some time to push the brake for us, and there's a typical velocity of a car, which then gives us a range which we need in order to assess a danger or distinguish a danger from normal objects. Yeah. Then there's this pre-crash idea, which is similar. So even if you have, because we have a delay in how we can push the brake, in case there's something coming up which looks like a crash, the car will actually pre-crash you. So it will brake, but not fully, but it will bridge, so to say, this gap in your reaction, so that in the case you really want to push the brake, you're still in the car, you're still in the control. but because we are lazy, we are slow, this is actually pre-braking, and then if it's not happening, you accelerate again, and that's it. There's a blind spot detection we talked about. It's a commodity. You can you avoid accidents by cars which are overtaking. And then the other thing is, which is mainly also an optical thing, is this lane departure warning. If you are sleeping and you're drifting to the other lane, something warns you. Yeah. And then also, which is a if you are in a stop and go and it takes time, then you get distracted, and then also the stop and go option can give you. And this is done at various frequencies. Be reminded, we do this at this frequency because we get the resolution. So for 77 gigahertz, we get the higher the frequency, the smaller the gate length, the wavelength, and in order to do that, this small wavelength will also increase our resolution, so we can see smaller objects. Why is that? Because in order to get some information about what this is, maybe in Freiburg here, a bike driver running into your path, and you want to have a warning, and you need to distinguish very nicely what this object is doing. So just the existence is important, but also some idea, is it turning or something. This is additional information you want to take out from that radar, because if you remember this just as an idea, here this object may pass without any problem very close to you, so this might not be harmful. The only thing what you need to have is to understand that it's approaching and overtaking, or it may be approaching to your car on a relatively small distance. So these are the critical criteria for building up such a safety cushion. And then the other idea is also that there's always sensors, and sensors have their pros and cons. And as I said, the forward-looking radar is penetrating very well, but also optical things like infrared and video, they have very nice features. Especially in the optical thing, we can do imaging much better than we can in the microwaves, and that's quite nicely. And then we can combine it with very easy sensors. So, for example, the ultrasonic is a very cheap and very reliable technique. So, especially what you have close to the car is sometimes better detected by an ultrasonic sensor, which just tells you there's a small thing standing next to your car, or you are just behind a wall, or there's a wall behind you, or something is not visible between the wall and your car. So this is what is helping. So it's always a sensor mix. Yeah, that's important. There's also major other functions related to that. So that's there's also some sensor here, which is of course also communicated and combined to by the cloud, which is for example, Alexa. But this is, of course, the main feature, of course, is the software. It's a learning tool, and the AI in that is strongly helping all these functionalities to be done. And that's just so in this sense, the microwave is a small function, but it's a major enabler in this case. So it's Bluetooth mainly, and it helps you to set up these sensor networks. Coming a bit to the history again, so we are talking about 5G these days, and what is 5G? What is this numbering? And maybe you can guess. So there's a historical thing here. We can look at that from the perspective that 2G came up in the beginning of the 90s of the last century. This was something which was, first of all, an analog mobile phone, nothing with data yet. That came a bit later, and then we went through the various generation with, first of all, sending digital messages, which was SMS. Then we are sending you first videos. Then with the onset of LTE, you see videos transmitted. And then there's also some intermediates. For example, we are now in a transgression of 4.5G to 5G. 5G is being deployed, and you see very naturally this comes every 10 years comes a new generation of mobile communication with major updates at about 5 years time. So this is something just to give you a feeling for what we are in here. What is new here so you always have to look at it globally. This is the Japanese perspective in relation to the European one. So you see things are alike, but especially the first thing is that what does 5G do? So first of all, we are typically with the communication, we are below 3 gigahertz, and the additions are now made expanding the frequency bands to higher frequencies than 3 gigahertz, which is what 5G is mainly doing. So you see here this 3.5 gigahertz band. So we add bands, and then depending on availability, you get major bands, and this is distinguished. You see there's different bands in the US, which to the European ones, which are partly overlapping, also in China and also in South Korea. And you see here, same thing for the band. So the technology is alike, but the individual frequency setting is very specific to the countries. It's mostly a historical thing. What is new here is that for 5G is that it's using the millimeter wave. So just to give you a feeling, we are 3 gigahertz is about a decimeter in wavelength, while 30 gigahertz is already a centimeter wave. So and anything which is shorter than a centimeter wave is a millimeter wave. So this is why we call this, it's the first time we're using millimeter waves in mobile communication. So already apart from the functionality, 5G is a major story in RF. And why is that? What do we have to learn? So first of all, we have to think about propagation, and there's various things that you can learn. So first of all, microwaves propagate in the atmosphere and also in space, and there's multiple ideas behind that. So first of all, there's the line of sight communication, which we sometimes use, but typically the communication we use is some reflections on the ground or even in the atmosphere, and or buildings help greatly to send signals around. But as you know, we can also, if we have the right angles and also the right frequencies, we can of course also communicate by microwaves to space. I mean, very prominently is the moon landing, which was looked at at about S-band around 3 gigahertz and X-band, which is 10 gigahertz. So this was sent out into space. And you see here that the atmosphere itself, this is also a basic idea, is serving as what we call a waveguide due to the density modulation here. The atmosphere is thinning, and that is similar to what we know from the optics, that a change in the density, or in this case by optics, it's really the refractive index that also allows a reflection here in the top layers of the atmosphere, so that without going line of sight, we can actually propagate microwaves through the atmosphere. That's just as a very generic idea why we're doing this. And now the first things I would like to talk about in this lecture is, what does frequency have to do with bits or data rates? And there's a clear distinction that we have a carrier wave, which is what we are sending. There's a single frequency or frequency melee, which is sent, and this is a regular thing. But this doesn't have any information on. So I will ask that question in the next lecture again. So if there's just a plain wave, except from saying I'm here, and not even that is specific, an unmodulated wave is not giving any information. Yeah. So it's like turning lights on. This is a carrier wave, but you cannot only like in TV, only if the signal is modulated, then you can provide information. So what you want to put on is the information signal. In the simplest case, for example, my voice, an audio signal, which then by some scheme of modulation is actually changing this carrier, not in the sense of significantly changing, it's still doing at that frequency, but we modify that carrier, and we call that particularly modulation. And what is the guiding principle? So the first thing is, what we are facing is, of course, that the data sphere which we are talking about is there's a driver. So we all are digitizing, or we are at least sending more and more information from simple phone calls to now big array clouds, which are a strong feature of severe data communication. And what we would like to be doing is to understand and support this exponential rise in data usage. Yeah? And you see it's still going up, and it's predicted, and always has been. This is also a law that the data communication is actually exponentially going over time, and that poses some significant questions to us. And why is that? So the first thing we need to understand is how the spectrum is organized, and then there is some basic rules, the theories of communication engineering, and I would like to talk about that. And the central idea is that, well, first of all, we already saw that the wavelength and the frequency are product, and they form the speed of light. And in most of the materials, with the which in the first instance are homogeneous like gases, we can also directly correct that for the index of refraction. And that's something which I would like to point to your attention to. So what is unique in this equation is the frequency. So we always talk about frequencies and not about wavelength, because on the path through the materials and through the channel, as we will later call it, the frequency is a constant. Yeah, so the frequency is always unchanged also by materials. So no matter whether I'm sending this through vacuum in top, or whether I send it here to some air which has a very similar index of refraction to the vacuum, or whether I'm going actually through materials, the frequency is always the same. What is changing is the wavelength. Yeah, so that's something we have to think about, and it's corrected by the index of refraction. But first of all, in vacuum, we'd like to speak a little bit about the relations. So microwaves start or transportable waves start very low. So you can have RF waves which are in the range of 5 kilohertz, which are similar to the audio frequencies. However, they can propagate, and they can be used because they are very long range, and they can actually be used to go through very long over very long distances, because also the attenuation might be weak. And you see here that we also some wavelength by heart and some frequencies. So for example, the classical radio is here in this range of megahertz. So what you can listen to in a car. And then we have classical television, not the one which we are getting through the satellite. And then you see here, especially the mobile communication, which is mostly, this is 3 gigahertz, is decimeters, and waves then continue to centimeter waves. Yeah. And the wavelengths are starting here for the very low 5 kilohertz. We are in the range of kilometer waves, so they are 30 kilometers or something long. So if you compare that to a building, you see also why actually these waves are not seeing any buildings, because the buildings are simply too small. While the frequencies or the wavelengths which we are seeing here in the radiocom, they interfere with the buildings. So that's because there's always this idea that the structures which we have in our path, if they come to the length of the wave, then it's getting interesting, because then some interaction starts playing. Yeah. And typically today the highest stuff we are using is in the range of 300 gigahertz, or maybe to a terahertz, so times 3 what we are showing here. This is the highest where we are looking at. Typically we have the most of the communication happens at 3 gigahertz, or maybe now starting at 30 gigahertz. But beyond that, things are the spectrum is quite unused. It's getting used more. You saw the radars, which we talked about at the beginning of this lecture. This was 77 gigahertz. Yeah, so this was useful, but beyond that, it's still in a research phase. And what the first thing we need to understand is the spectrum is not freely available. It's allocated because we don't want one application disturb the other. And you can ask why are we not speaking freely? Yeah, it would be annoying if communication was um, interfered with by some others. That's the first thing. And the second thing is there are simply some functions which we don't want to be jeopardized. So medical emergency frequencies, like the connection to the helicopter, which is getting you to the hospital, should not be uh, hampered with. And if you do that, there are strong fines on that. Here it's given for the United States, so you start, and every band is, so to say, an application. It's very historical. You see, it's quite crazy here. Some things are really crowded, and some others are just blanked out for usage in specific applications, as I just started to understand. And one thing you have to understand, if a spectrum is taken, that is something which I just would like to remind you of. If a spectrum is taken, you cannot use it for something else. So it's like this means that spectrum is a resource. It's not something which is freely available, because if it's taken, it's not there. And the only option is to go to a different part of the spectrum, typically going higher. So you saw that already with the 5G, that if we are going up to about 6 gigahertz at the moment, and then there's a large gap till 24 gigahertz, because other applications are covering those bands, and we cannot use them at the moment to do radio communication. And here, for example, there's the Frequenznutzungsplan in Germany, and there's a couple of things related to that. So the first thing is that you learn is there's the frequency, and then you see the application here, TV, radio, and then there you also see that depending on what application you use, there's strong changes in the maximum allowed power. Yeah, so you see that here for some things like TV, you can set up several hundred kilowatts, while for a simple your personal radio communication, you're only allowed to do something like 4 watts, or at least, and that is strongly changing. So that's something. And yeah, and then there's also the modulation which is allowed, and then whether it's a pulsed or a CV application is also continuous wave application will also be regulated. So you have to be very careful when you start radiating it. You will maybe facing some trouble. And what we are going to talk about now is to help you into all this stuff. This seems to have some strong structure, and the question is, why is that so? And the first thing to learn is that the understanding of the traffic, so the information or the bits represented by the bits, this is, as we said, growing. And now we need the idea of this channel capacity, or these increasing number of bits relative to the frequency. Yeah? And that was looked at very early in the process by a person called Shannon. And the principal idea is that you have an information source which you transmit, and along that channel, before you receive that, there's something happening. And then the question is, there's all kinds of problems which can arise on this channel here in the middle. And the main finding was that for the limit of this capacity, which you have for a certain piece of information, that this is limited mainly by a factor which we call noise. Yeah, so this limit is limited. All other things are impairing below that, but the fundamental limit is the noise, and that is relatively simple. So what Shannon predicted and also found was that that this channel capacity C is essentially there's two main findings in this equation, that this is proportional to the bandwidth. Yeah? So that means that if you go back here, if you have a fraction of the spectrum, that, for example, from here to here, you can, in absolute, only transmit so and so much. If you have more bandwidth, then the channel capacity in the bits increases linearly. Yeah? So that means, for example, if you have between 1 megahertz and 2 megahertz, you have 1 megahertz of bandwidth. This difference, this absolute number, is proportional to the capacity of the bits which you can transport through that particular spectrum. Yeah? And that is the limit. Yeah? And then, because we are talking about noise, there must be, of course, some relation to the signal and also the signal strength. It cannot be fully independent, because it's clear that if there's no power in this spectrum, in this signal, relative to the noise power, which is always there, then there's also no channel capacity. So it's like you can understand this like you have a noise floor. And what is this noise floor? It's essentially a power over frequency, which is just there. So in order to get a meaningful signal transport, this power which you're looking at has to be higher than this noise floor. We'll come to the sources of noise a bit later, but first of all, to explain what we are talking about here. So when I have a power in the channel, for example, a microwave source or a laser which is beaming, then this has to be higher than the noise, this power, in order to get any meaningful capacity. Yeah. This is not so visible here, but so just to explain it here. So the idea is that when we are having a power, in order to peak out from the noise floor, which we in the first order we assume to be a constant power floor over frequency, we assume that you have to have this signal which you are transporting, the carrier wave, over the noise floor, and only then there's a useful signal strength visible to the receiver. And what is the issue with that is to understand the mathematics of that. Yeah? And normally you could say you're transporting more power if you're speaking louder or if you're sending harder with the radiator. Yeah? However, what you learn from this equation is that what comes out of the system, which is because the noise is also amplified, you always have the signal plus the noise over the signal, which is and this is in the term of a log function. Yeah, so if you're speaking louder, the effect on the channel capacity is only by a log, so it's a sublinear behavior. Yeah, so if you're speaking louder, the channel capacity does not go up linearly with the power, but only by a log function, which is a weak function. So it helps to speak louder, but it's not necessarily helping in the way you may have hoped for. Yeah? And that has and there are several other reasons why we can't just put up the power to increase the capacity. So let's assume we have a given bandwidth, so we get 1 megahertz of bandwidth, and we want to still increase the capacity, send more bits over that. And if you now increase the power, if the noise is given, you could do that. But there's several other limitations, and one you can observe, for example, in your microwave oven. It's the same frequency which we use for radio communication. It's 2.4 gigahertz, so very comparable to what we are doing in the mobile bands next to them. And typically your cell phone is in the range of maximum a watt or 2 watts of power. The base station is maybe 100 watts of power, and that is good, and that is limited. We need that power to organize radio communication. But for example, if we use a kilowatt close range to some tissues or something which is human or biological, then you can observe in your microwave what's happening, because if you get a piece of chicken or a piece of meat very close to the 1 kilowatt of power, which you may have in your microwave oven, you know that this first starts heating, and then if you do this continuously, you see the biological effect of that based on the close distance. Yeah, so this power which is imposed here cannot be drastically up, because somewhere here in the increase of the power you will start frying the atmosphere. Not counting how you make that power. There's also a limit in the prime power to make that microwave power. This is of course also a limit, but the biological effect is very clear, and which is why for most of the application we have a maximum power which is allowed here, because here, for example, for TV, there is also an assumption how this power is transmitted. You typically don't find a TV station in a urban area next to buildings. It's typically out in the country and very high in the sky, and then to transmit over longer ranges of at least 50 kilometers. Yeah, so that gives you the first flavor, and then if you rewrite that maximum channel capacity, and that is the theoretical maximum you can get for the bandwidth. Yeah, that is to say that we introduce something which you, I think, know already. This is the signal to noise ratio. So when you rewrite P plus N over N, you can write 1 plus P over N, which is the channel, which is simply the idea that the capacity is proportional to the um, bandwidth, and if you increase the power, you add something, and what is added is defined on the ratio of P and N. So you can increase the power, and you could have low noise, but noise is always there because it's a temperature effect, and you know that noise in the environment is essentially an idea that is related to us being at a finite temperature. So you cannot really reduce noise. The noise is always there, and the only real way to reduce the noise is temperature. So you can go to lower temperatures, but that's not such a useful concept for daily living, because biological human beings need a certain minimum temperature in order to provide their body functions. Yeah. So the N is a constant. You can keep it low by not adding noise. We will do this in the transmitter because that's also very clear that there's not only noise available, but all the components which are in the path also typically add noise to the process. So that's not something which is constant. And so it's keeping noise down rather than reducing noise, which is the idea. And so then the question is, for a given power, because we cannot fry our environment, the only way to increase capacity is to use bandwidth. And that is the fundamental idea. So so this function, which is essentially the channel capacity, which is exponentially rising, this means that we also need an excessive use of bandwidth. First thing is that we use the existing bandwidth at the Shannon limit. So we are getting very close with mobile communication to this theoretical limit. So this is the theoretical limit which we're having here. So this is the maximum you can get. It doesn't mean that we always use it, but in the mobile comm we are approaching this very clearly. And let me give you some very clear examples where you can see the ratio. So for example, in this TV channel, which I was talking about last week, there's the satellite channel, and this is actually quite a powerful system. So it is a system which has a signal to noise ratio of 20 dB, which is a factor of 100. And assuming that you use a video bandwidth, which is this bandwidth which we're using of 10 megahertz, then the channel capacity can be calculated to be 10 million hertz times the log of the signal to noise ratio plus 1, and that comes up with a relatively surprising high data rate of 66 megabits per second. So that's not nothing. It's by now it can be also taken higher, but it's a significant data rate, which explains why you see something on your television. Yeah, so that gives you, and here you see that it's really the absolute bandwidth. So it's really the difference between 10 gigahertz and 10 gigahertz plus 10 megahertz. And so the 10 megahertz is actually counting and making up the pace here, or the channel capacity. Yeah. And then there's a second theorem which helps us, which is very important to be seen. So the question is now, if you have the absolute bandwidth in relation to the carrier frequency, there's something which we need to also to understand. That is that there's a second theorem which is also partly attributed to Shannon, and it's the Nyquist-Shannon idea, that the sampling frequency which we are using in a information transfer needs to be double the maximum frequency of which we are transmitting. Yeah? And we will encounter that idea in various settings later on. So for example, just to give you an idea, your audio CD, which by now is also a very outdated concept, the maximum frequency you need to transport is the maximum of our audio. So if we are very good in hearing, we can hear 20 kilohertz, which for most of us is not true anymore, but it's a possibility. And that's why the sampling frequency of this system has to be twice that. Yeah, so the sampling, and this is the case, and for the audio CD, the sampling rate is 44 kilohertz, which is higher than 40 gigahertz, which would be the idea. And here you see why this is needed. So if we are not sampling with the right, if we have an undersampling, which is something which should not happen, then you see that the real wave, the F, which is the black curve, and if it's sampled by something which has a sampling frequency much lower than the black curve, the blue curve, for example, then you see that you're creating from this something which is much lower in the frequency, and that wouldn't work because this criterion is not fulfilled. Yeah. So you're building something which is not reconstructed well. Yeah. So you need this factor of 2, and we will encounter that very often. So that is needed. Let's talk a little bit about this channel capacity. So this channel capacity is simply it can be either analog bandwidth or digital, can be data rate. So that's something both is possible. So it's the same idea. Yeah, and the channel capacity is proportional to the bandwidth with the power in between, as we said, and there's several things which you need to learn, and that's the first thing is that an obvious concept of usage of the spectrum is to distribute the spectrum to all of us. So if you do this, you will first of all have some bands, and everybody of us gets a fraction of the spectrum. So let's assume we have 10 megahertz for something. So if 5 people in the room, everybody gets 2 megahertz. What you learn is this may be a sound concept like in a walkie-talkie. There we do that. Everybody gets a quartz, and then we are getting all our spectrum. The problem is that this distribution of the spectrum is a very bad one. So something sharing by dividing the spectrum in shares is not a very good idea. Yeah, so because you are far away from that limit of the Shannon spectrum. Yeah, that is something. And what does that have to do with the Nyquist? The Nyquist is that at some point when we are transmitting, We also have to make sure that we are, when we are in the channel, that the bandwidth of this channel is also not falsifying not falsifying our transmission. And we will see some cases where we need to make sure that we get sufficient transport over the channel to do some communication. Um, the the separation, assuming that we are distributing the channel, the spectrum, is not efficient, maybe, but it's maybe also an idea of spectral. There's also an idea of spectral masking. Yeah? So as we learned earlier, when we are you saw that we are distributing the spectrum into applications. Yeah, so band 1 may be communication, band 2 may be the microwave band where we are frying and using medical applications and all kinds of other stuff. 3/3 may be a radar band, the green one, and the 4 may be some other communication. And of course, the idea is that we will distribute the spectrum between application, which is something else than the usage on the modulation side. Yeah. So for example, here, if we are in this band where we are strongly sending out microwaves with the ovens, there's one thing we definitely have to do, that if we do that within the band, we have to make sure that nothing overlaps into the other spectra. So for example, the microwave oven. So how can this work here? That is something which is a bit uneasy. So here we have something which is which sends at a couple of 100 kilowatts, and there's something which the CB radio communication only works at 4 watts. So what we have to definitely avoid is that there's spillovers. Yeah, so there should not be from this band to the other band, there should not be any transmission. And some people, for example, there are some extreme cases where you understand the problems. So, for example, when you have a band for space science, where they are listening into space, these overlaps, if you have in the nearby band, if you have any form of radio at all, you should not have a spillover when you're listening to extremely weak signals, because you have strong transmitters in the vicinity of the not in the vicinity as such, but in the vicinity of it's seen in the frequency. So if you are radiating here strongly and you want to listen here very closely, we need to talk about the fact how much allowance is there that things go over from the frequency. And there are several nonlinear effects, which we will cover later, which are physically putting power which is here into the other spectrum. So this is a bit dangerous. Yeah? And the idea is, by defining these differences here, is called spectral masking. So you say there's first of all a range where we can use one application, but there's also the bands where this band may not put power into the next band. And who is going to tell us this? There's several institutions, and there's first of all the standards. Yeah. So when we apparently we have agreed on something, this is the ETSI, the European Telecommunication Standards Institutes, which gives us these limits. Yeah. So for example, if you are here with your, let's take some critical things, they are simply, for example, in the car traffic, this is a good one. If you're operating a radar in the 77 gigahertz band, there will be simply a max power for this radar, because if this radar puts out too much power and goes beyond these 200 meters that we earlier talked about, then cars which are far away from the car which you actually want to detect will be affected, and that requires some regulation. Yeah. The other thing is also that for some things we need high power. for example, for talking to ships or to airplanes or even to satellites. And then we need to make sure that not only the power is regulated, then also where it's radiated. For example, it's not a problem to send out large waves somewhere as long as you're not sending them directly to the ground. And that's, for example, how radars are operated. When you, for example, have here a radar system, it will not, if it's directional in the air, then it will not be harmful. If it operates downwards, then the people next to the radar might be critically affected. So, because if this was an airport and this is he's trying to see a plane which can be far out, then here you can have larger powers as long as you're not looking downwards. Yeah, and that helps you to understand why we need standards in order to make life useful. And then we have several others. Just there's a sequence of people. There's the Bundesnetzagentur, and these are the people you talk to when you violate those rules, and they sue you. There's the ITU, which is the Worldwide Telecommunication Union, and then there's the people like the IEEE who are defining the standards. And so, for example, here the standards are then defined by some people like you. Later in your career, you might be doing that, and that's why things work. Yeah. The question is now, when we are having such a system now, how to reach maximum data, or how do we get closer to this channel? And the channel capacity is, first of all, there's now various ways how we can do that. And for example, there's also a learning. For example, when you look at your grandma's old radio, you get the easiest thing of radio communication. You have an amplitude modulated radio, which is simply something which is capable of sending radio waves and in this case receiving them especially. And there's now two ways of doing that. So the first thing, how this first radios were doing it is there is an incoming microwave, and you can of course now detect in the antenna, you can detect this, and you amplify the signal first of all because it's weak to keep it above the noise floor. Then you have two choices. You can either directly look at the signal, that would be the homodyne case, and here, because in the beginnings people didn't simply have radio components, so they had to down convert as fast as possible to be able to do something. So what they were doing was you mix the signal down, and it sounds very technical, but effectively what you're doing is there's a radio wave coming in with an amplitude modulated signal on top, which may be the voice. Yeah, so that's how the first radios worked. And in order to do that, you would put a local oscillator next to the incoming RF frequency. And the difference, this use signal, which is simply the 20 kilohertz audio signal, is the difference of this RF frequency minus the LO. So you would put the LO very close to the incoming signal, and the difference would be the directly detected audio signal. Yeah, so this demodulation, which takes out the information, so to say, the voice information from this modulated signal, that sounds now very technical in these block diagrams, but effectively it was just a down conversion. Which so essentially you're getting a frequency, you're putting one which is very close, a bit lower to it, and then you can take out the information directly and listen to it on this radio. So this is and because this is a concept which is played from the idea of cheap components, not available components. Yeah, it's still quite useful. It's not, don't get it wrong. But that's how all this started. Yeah? So this is the heterodyne concept. The other concept is the homodyne, which is, it's not a secret that we're using this for our mobile communications and especially for your cell phones. Yeah, and in this case, you have to given a low power, which you have in your personal device, there's an incoming wave. The first thing is that you have to find the frequency which is incoming, but that's possible, yeah. And then, without further notice, you directly demodulate, yeah. And so you track the incoming frequency, and by doing something smart, and that's what your cell phone is doing, you directly get the demodulated signal and the data, in this case maybe audio data or bits, and you can further use them. So we call that zero IF reception, because there's no intermediate frequency. It's a direct demodulation, and that is what your cell phone does to the maximum. And we will, because the trick is, that's what you're learning from this is these are all components. And this, for example, here in this case, I said there's a filter and an amplifier, but in the easiest case, this is all non-existent. So essentially, you mix it down, and there's no demodulation, because the signal you get from the mixer is directly the down-converted audio signal. So you don't have to do anything, and it's just in components. It's very simple. It's just to show you the functions. Yeah. Okay, and then, as I said earlier, what is not smart is to do some things which are obvious. So, for example, the amplitude modulation and the is the easiest way. So you have a carrier and you have a signal, and between them you want to put the data on the carrier. So the signal is gotten from the carrier by just changing the intensity of the carrier. That's an very easy way of doing that, which we call amplitude modulation. And the other thing, which is very similar, is just to use the phase, but that is already harder, because you need something like a phase detector to do that. So technically, it's a bit more complicated. Amplitude modulation is easier to do. And asking you, what are we doing these days? The trick is, and maybe I explain that from the idea later. What are we doing these days? We are doing both. Yeah. So here is a simple form of modulation, and here in the for example, if you now want to put bits in a digital modulation scheme on a carrier, the first thing is to do phase modulation. Yeah. So you're giving you're looking at the modulated signal, and you're trying to talk about information flow. And now the question is, how do you get bits on a carrier? Yeah, and the idea is simply that the 1 in this case is represented by the 180 phase relation, and the 0 is represented by a phase of 0. Yeah, so if this is the phase angle here, this is 0, and this is 180. This is a simple form of phase modulation. Yeah. And that is a binary phase modulation. And the trick is now we can continue to do that. We can make it a bit more complicated, so we can have smaller angles for the representation, and we can have also multiples of this. So you can say you modulate both amplitude and phase. Yeah. And coming back to the beginning, question is, when you look at this, and this is something you need to think about a bit, if we are using whether we are using amplitude modulation or phase modulation, you could ask, what are we using? And the answer is both. And now, what on earth does that have to do with channel capacity? Yeah? So coming back to this modulation and to the beginning, and that's how I want to close for today, is this is a theoretical limit. Yeah. So this is what we can, if we have a certain bandwidth and power, this is what we can achieve as a maximum. Now we do this in reality, and we realize that our channel capacity, which we are getting, for example, by pure amplitude modulation and by phase modulation, is very small, very weak. Yeah? So we are not making use of this maximum capacity in the beginning. And the trick is now that by using more complex modulation schemes in amplitude and phase, as I was just starting to indicate, we are approaching the channel limit. Yeah. And why is that? Because what we need to do at the end of the day is to accommodate the need. All the people around us are asking for all this data. Yeah? But we only have so and so much bandwidth because there's simply spectrum is simply not available. Yeah? And now, in order to make that life better, we are trying to use the spectrum we have as efficiently as possible. That is at the Shannon limit. Yeah? And at the Shannon limit, to get there, we are inventing modulation schemes which are more complex. So it's a mixture of amplitude and phase modulation in a digital scheme to put as many bits as possible on the given bandwidth. And how can I see that? When I have a certain bandwidth here, the number of bits I can put on for a certain bandwidth is depending on the modulation scheme. Yeah? For example, here, the difference between this modulation scheme, where you have a difference in the phase angles between 0 and 180, this is quite coarse because it's just phase or antiphase, which is an extremely strong difference. Yeah? Here, in this case, the difference is only 90 degrees between the individual states. Yeah? And the question is now, why on earth am I doing this and not the other one, which we had before? And the answer is because this is giving you more bits. Yeah? So this can only represent 1 bit, and this can already represent 2 bits. Yeah? And now you can play this game till forever, until you get to a very small difference, that you're putting more and more bits on this particular bandwidth. Yeah? This is the phase shift keying. But as we do with the QAM, as it's called, then we can not only change the phase angle, but we can also change the amplitude setting. So we are not doing 0 and 1, but we are doing 25%, 50, 75, and so on. Yeah? And by getting coarser and coarser and by getting finer, we are approaching the Shannon limit. And that is good because only then we can make use of the existing bandwidth, and your internet and your data connection is faster. Yeah, and here are some application use, for example, for the TV. This is the thing for the DV, the terrestrial television. Yeah. And 16 QAM, as it's indicated here, is already a relatively coarse thing. So the modulation you're using when you're now looking at your cell phone is more in the ranges of 256, 512, and 1024. Yeah, so that's just something I would like to counter. So what you learn from these simple considerations, there is a maximum we can get. We are trying to get closer to that by better modulation, and we are trying to get as much channel capacity as we want. And one thing we also learned is we can't do much about the noise except from keeping it low by good components, for example. And the other idea is that when you increase your power in the system, this might increase your channel capacity, but only to the limits of the biological and energy efficient means. Yeah. So we don't want to build a 5G system which is frying people or which is even causing harm to people or to any human beings. Yeah. So that's what it is. I'll stop here, start thinking about it. It's not so difficult, but I hope it clarifies a couple of items which are now starting to get sorted in your head. Yeah? So thank you very much for your kind attention, and I'll see you live on November 2nd in the room. Thank you very much.